Okay, folks, we're going to get things underway. So good evening. Welcome to the 32 people that are online and about 50 that are here in person. It's great to be back in person here this evening. My name is Dave Chisholm, and I'm the president of the Ottawa Centre, RASC, and I'm the interim meeting chair. And I'm hoping by January we'll have a real meeting chair. So let's see what's up for tonight. My clicker's not working. Okay, so a special welcome back to the Canadian Aviation and Space Museum. Let me try my clicker again here. There we go. So we are recording this webinar for posterity. It will be available at ottawa.rasc.ca. For those online, please use the Q&A box to ask a question to the speaker. Chat box comments, we're not going to be monitoring them, but they will be seen by everybody there. And raise your hand is disabled, except for the folks in the auditorium here. I can't prevent you from doing that. So the RASC Ottawa Centre acknowledges the trust placed in us by our First Nations with their ancestral lands and sky. And my clicker is not working again. Okay, here's tonight's program. And so we're going to have Nathalie before the break, have AstroTrivia, and we'll probably take about a 10-minute break because we have to use washroom facilities here. Oscar will be speaking after the break. We have a number of observation reports, monthly observation challenges. And because we are in person, we are back to having the door prizes. So the door prizes are available to anybody, whether you're a member or not. At the break time, please come and see me. I have a roll of tickets right here. And we'll be calling out the ticket numbers at the end of the meeting. You're welcome at break time to browse the door prize table, see what's there. And there's also a please take it away table over there with books that people have donated that are not part of the door prize, and you can take as many of those as you want, please. Okay, next slide, please. So welcome to our new members, and we have, I know Kevin's here for sure tonight. Are there any other new members in the audience? I can't really see. There we go. I see a few hands up. So welcome. And we have 76 new members in 2023. Next slide, please. Members in the news. Andrea is here. She can wave her hand wherever she is. Okay. So Andrea made the cover of the Observer's calendar for 2024. So congratulations. I think Andrea is buying 50 of those for Christmas presents for everybody. Okay, next slide. So just to encourage those who are not members, if you'd like to become a member of the RASC, the regular membership is $103 a year. Family membership's $97.50, $16.90 per adult, $9.20 per youth. And if you're a student under 25, the membership is $62.40. So what do you get for your membership? Well, the benefits, local benefits that you have here are the Ted Bean Loan Library. And we've recently refreshed this library with some brand new telescopes, at least brand new to us. Peter Schutt's been doing an amazing job of refurbishing all of them. And we also have our private observatory just the other side of Almont, near the mill of Kintail. And we also have, finally, we can come back into the museum here, and we have the Stanmont Book Library. That will be available at the end of the meeting tonight, and Estelle will guide you there. It's behind the curtains here. Next slide, please. Nationally, then we have the journal that comes out. You get that electronically. We've got a hard copy of the Observer's Handbook every December. Locally, we produce some really good astronotes. Gordon Webster is our editor for that. And that comes out electronically as well. You can get a hard copy version of the journal at extra cost when you renew your membership. Next slide, please. But the biggest benefit here at the RASC are the people and all the people you meet. And those who can, if you're new to astronomy, there's lots of folks who'd be quite willing to help you with your first telescope, or if you've got a telescope, trying to figure out how to use it. Next slide, please. The annual general meeting will be held as part of this monthly meeting on December 1st, 2023. Notice will be sent to all members by email and will be published in Astronotes on the website. The annual general meeting typically takes about 30 minutes, so please don't skip the meeting. We'd love to have everybody here, and we have additional presentations after the meeting has concluded. Next slide. Stephen Norse, who's in charge of our nominating committee, is responsible for getting names for the election of the officers, councillors, national council reps, meeting chair, and those elections will take place on December 1st, 2023. A lot of the other positions are appointed by the council itself. Next slide. So here is the results of the nominating committee. So president and director, that's myself. I'll be serving the second of a 2-year term. Vice president and director Oscar is again serving the second year of a 2-year term. Secretary and director Chris Tarrant, he's in there for life. Treasurer and director Richard Taylor is continuing on in this position. Now the folks, the secretary and director, treasurer and councillors, all these are up for election. So if you say, okay, I really want to be secretary, well, by all means, put your name forward, or treasurer. But we want to try to make sure we've got the names filled. So Katie Francis is returning as a councillor. Tim Cole has volunteered to step in that position. We do have one open position. That's something that interests you, speak to me, or Stephen Norse. No, Stephen Norse is online. Speak to me over the break, and we can fill you in on what's involved with that. Mick Wilson has decided to return as a meeting chair. He had to take this year off, but he's quite happy to come back, and I'm looking forward to that. Past president is not an elected position. It's Stephen Norse is completing a second year of a 2-year. He's also a national rep, and we have 2 more openings for national rep. If that's something that interests you, we could be glad to hear from you. Our financial auditor is Paul Sadler. Next slide. Nominations may be submitted for any position. Nominees must be members in good standing. National representatives must be at least 21 years of age. Nominations must be supported by 2 members and sent to the secretary, Chris Tarrant, by 8 p.m. on November the 26th. Secretary at ottawa.rasc.ca. Again, you'll be getting an email regarding this as well. These are the appointed positions, and these are appointed by council. We currently have the hospitality position open. I think we have somebody who might be interested in it, but we have to confirm that. But hospitality basically is you set up a table outside in the lobby here after the meeting, and you provide cookies and coffee and soft drinks, and it's an opportunity for us to meet and greet. Next slide, please. The other thing that we are working on are the awards. And if you're interested in being part of these awards, please contact myself, president at ottawa.rasc.ca. And if you want to submit a planetary observation for the Rolf Meyer Award, Observer of the Year, again, if you want to submit, please submit them to me. And the observation reports at the monthly meeting are automatically considered in this category as well. Next slide. Oscar.
Hey everyone. So we're the annual dinner meeting is making a return this year after a 3-year hiatus due to COVID. So this year it's once again going to be held at Algonquin College on Friday, November 24th, 6 p.m. Cocktails, starting with cocktails at 6 p.m. and 7 p.m. dinner. Afterwards, we'll have a talk from our guest speaker, Dr. Sarah Mazarui. So I'm selling tickets today at the table if anyone wants to see me during the break. They're $65 or 67 if you're paying by plastic here. Yeah, and I just want to give a shout out to our sponsors, Diffraction Limited and Conscopes, who very kindly have supplied some very nice door prizes for the annual dinner meeting. Yeah, so looking forward to seeing as many of you there as we can possibly get. Thank you.
Now, we do have some calendars available here tonight, or if you've pre-ordered your calendar and said you're going to be picking it up, Oscar will have those available at the break and at the end of the meeting. Chris, I'm noticing online that we are not seeing we're seeing the presenter's view and not the full slide view. So I'm not sure what's going on there, but when I look at on the Zoom. In the meantime, we'll just keep on moving forward while Chris figures that one out. And the clickers, there we go. Ottawa skies. That's me. So here are the moon phases for the month. We switched to standard time on Sunday, which is great. That means we can start our observations an hour earlier. The new moon is on November the 13th. And that's the best time for doing our nighttime observing. Full moon's on the 27th. This phase, this full moon is known by early Indigenous peoples as the beaver moon, because this is the time of the year to set beaver traps before the swamps and rivers froze. It's also been known as the frosty moon and the dark moon. The Northern Torrids meteor shower is tomorrow night, overnight to Sunday. It's a 5 to 10 meters per hour, so it's not a big shower. And the second quarter moon may block most of the dim meteors this year, but if you're patient, probably the best time is to view them after midnight. Looking at the clear sky charts, mixture of clouds, but you may be able to catch them. Next one is the Leon's meteor shower, November 16th and 17th. They're about 15 meteors per hour, and the crescent moon will set before midnight. And so that would be a best time after midnight to see that. The sun rise and set. You'll see a dramatic jump in some of the times here. That's because of the switch to standard time. But obviously the days are getting shorter. Mercury is rising and setting with the sun. There's no elongations this month, so it's pretty well not visible to us. Venus is visible before sunrise. Mars is not visible at all this month. It's rising and setting with the sun. Jupiter is visible in the evening. And November 3rd, it's at opposition, best closest to the Earth. Saturn's visible in the evening. Uranus is visible in the evening and through the night. November the 13th is at opposition. Neptune is visible in the evening and through the night as well. So when you see these times on my slides here, the first time set is the first of the month, and the last one is the last of the month. And here is my cartoon of the month. A universal remote. There we go. If things could only be that easy. I'd like to have a cloud remote. That would be awesome. Okay. So I'm very pleased to introduce our guest speaker for this evening, Dr. Nathalie Ouellette, and she's going to be talking to us about the Webb telescope. And she's an astrophysicist, avid science communicator, and her research is on the formation and evolution of galaxies, particularly those found in groups and clusters such as the Virgo cluster. She's a coordinator of the Institute for Research on Exoplanets and the outreach scientist for the James Webb Space Telescope in collaboration with Canadian Space Agency. She says, I take science very seriously, but I try not to take myself too seriously at the same time. Science has to be approached with a rigorous work ethic and a sharp critical thinking, but it's also just so much fun to do and talk about. I hope my love for space will come through here, and I'm sure it will. So welcome, Nathalie. We're just going to take a second while Chris stops sharing and Nathalie shares her screen. And let's hope the technology works.
Thanks so much. I've shared my screen from my side, so just let me know when it's visible in the room over there.
Okay, Chris, we're still seeing your screen. Just give us a second here.
Sure. It seems like people online, at least, can see my screen.
Yeah. Okay, we're good now.
Okay, perfect. Thank you. So thanks so much for the invitation. This is my third time speaking with RASC Ottawa, and my second time talking about the James Webb Space Telescope, but the first time was now 4 years ago. So an immense amount has changed since then. So I'll give an overview of the basics of the telescope, but of course, there's just a huge wealth of discoveries now and science that we've been doing now that the telescope has been launched and has been working wonderfully well. So we're not only thinking about unveiling the universe with the James Webb Space Telescope, but we're actually doing it now, which is really, really exciting. So talking about telescopes, I always love talking to amateur astronomers. Really, you're so much more knowledgeable than I am about the night sky when it comes to going outside and looking and using these small telescopes and everything. So it's a great testament to this huge history and all this culture that we have around telescopes and astronomy in humanity. The fact that telescopes have been around for hundreds of years. But of course, over time, we wanted to go beyond just the visible light. And in order to do that, we need to use specialized telescopes that can see what the human eye can't see. So we have telescopes that can look at visible light, just like human eyes, but the electromagnetic spectrum, very, very wide, holds all different kinds of light that are invisible to the human eye. So this goes from very long wavelengths like radio waves, which we often associate to sound, but it is a type of light, through infrared light, which is the type of light that the James Webb Space Telescope can see. Of course, visible light is still part of the electromagnetic spectrum. And then the shorter, more energetic waves like ultraviolet, X-rays, and gamma rays. So humans can't see in the infrared. We radiate in the infrared, but we can't see through it. So we need a specialized tool like an infrared telescope, like the Webb telescope. But it's more complicated than that, however, because if we want to look at infrared light and other kinds of light, we need to have access to that radiation. And here on Earth, we are surrounded by a protective atmosphere, which is on the whole a good thing, but it's not as good of a thing for astronomers who want to really harness the power of this light. So here you have a graph showing how opaque the atmosphere around us is to different types of light. So the more brown you see, the more there is blockage of that kind of light. So here you have the very short wavelengths, gamma rays, X-rays, ultraviolets, they're completely blocked out by our atmosphere, which is a good thing because they are actually quite harmful. They can destroy cells and mutate DNA, so we don't want those things. We want to be protected by them. There's a very nice window in the atmosphere in the visible light, which allows us to see, and also in the radio waves, which we really harness for our telecommunication systems. If you look in the infrared, it's quite patchy. That means that there are certain types of infrared that you can see through the atmosphere, but not all, especially when you go into mid and far infrared. And even in some parts of the infrared where you do have some transmission through the atmosphere, it becomes dicey because our own atmosphere is also glowing in the infrared. So infrared telescopes can get all confused on Earth, and they have a hard time discerning what is signals from our own Earth and what is signals from celestial targets out in space. So one way to get around this is to put a telescope up in space. It's complicated, it's expensive, it's risky, it's difficult, but the reward is huge because then you don't have any of those issues dealing with the atmosphere or with weather or with clouds, which is something you're all too familiar with, I'm sure. But there are different dangers in space, like micrometeoroids that hit your mirror and damage your mirror. And if something breaks, you can't access the telescope, you can't fix it, especially in the case of the James Webb Space Telescope, which is 1.5 million kilometers from Earth, so much farther than any human has been, and too far for us to fix it. So we often call the James Webb Space Telescope the successor to Hubble. Hubble, a wonderful machine that's been working for nearly 34 years now, that looks at the visible light in the universe, so sort of like the human eye. And it is in space as well, and has been repaired and updated and made better numerous times over the years. But it is getting old, and so a successor, not a replacement, but a successor has been in the works for a long time. And they're very complementary machines because they look at different kinds of light, so different kinds of phenomena. They can bring different points of view to studying space. So finally, the James Webb Space Telescope was launched in 2021. It is an international collaboration led by NASA, but with important contributions from the European Space Agency, and both of those were the partners for Hubble. But more excitingly for us, the Canadian Space Agency is a part of this collaboration. And this is the largest space astronomy mission that Canada has ever been involved in. And certainly, I hope, simply a blueprint of things to come. So I do very much hope that Canada is involved in the successor to the James Webb Space Telescope. So as mentioned, I'm the outreach scientist for the Webb Telescope. This is a relatively new kind of title that exists in a lot of different research teams. I have a background in astrophysics, and I specialize in the formation and evolution of galaxies, but I act as sort of a bridge between the scientific team in Canada and the general public. Of course, it's public funds that has allowed Canada to participate in this mission, and we truly believe that this telescope belongs to the entire world, especially the countries that contributed to its instruments that have been leading to all these wonderful discoveries. So I have the pleasure of working closely with Canadian scientists that contributed to the instrument, the Canadian instrument aboard, that are using data right now from the telescope, that are doing science. And I'm making sure that the public has access to all those discoveries as well. So I've had lots of chances to work with lots of great people, and I even had the chance to visit the telescope in 2019 before it was launched, when it was still being tested in a lab in California. So that was wonderful. So it's a huge telescope, and I mentally knew it, but when I saw it, it's really when it clicked. It's a small house that is floating up there, taking all that data in space. So it was a really great experience to see it there. So of course, its iconic piece is the big golden mirror, which collects that infrared light. But all of that is redirected to the box at the back of the mirror, which holds the science instruments on aboard Webb. So there are 4 instruments in total in this box. You have NIRSpec, which specializes in taking spectroscopy of celestial objects. You have NIRCam, which is really the big money maker in terms of taking beautiful, breathtaking images. So there's a good chance if you've seen a beautiful image taken by the Webb telescope, it was taken by NIRCam. You have MIRI, which can take both spectra and images, but looks at the mid-infrared, so slightly longer wavelengths than all of the other instruments. So very complementary. It looks at different kinds of phenomena. And at the very center, you have the Canadian instrument, FGS NIRIS, which is in fact a double instrument. So we have a double contribution aboard Webb. It's this piece, this golden box at the center of this image where it's being tested. It's about the size of a dishwasher. And on top, you have the fine guidance sensor. So this is the guiding camera aboard the telescope, which allows the telescope to find and lock on to its target with great, great precision. The most precise guiding camera we've ever deployed on a space telescope. And that means that even though it's not a science instrument, every single image that we take with the telescope has the quality that it does because of the high accuracy and precision of the Canadian guidance sensor aboard the telescope. So a critical piece of the mission. On the underside, you have NIRIS, or the Near Infrared Imager and Slitless Spectrograph. They can take both images and spectra in the near infrared, and it was built as a machine specialized for two things: the study of exoplanets and their atmospheres, and the study of distant clusters of galaxies. So it can take spectra of 1,000 galaxies simultaneously. It is the instrument that could take the most spectra at the same time from all of the different instruments aboard Webb. So this was a huge collaboration in Canada. Hundreds of people were involved at the Canadian Space Agency, where I work at the University of Montreal, the National Research Council, the Hertzberg Center in Victoria, and our main industrial partner was Honeywell Canada. But there were, even beyond these institutions, people from other places in Canada contributing to this. So that was an overview of the telescope, but of course, we're interested in what it can actually see. And one of the things I love about the Webb telescope is that it is a very diverse tool. Some telescopes are specialized in doing only one kind of science or studying one kind of object. I can think of the Kepler telescope, for example, that only looked at exoplanets, or the Gaia telescope, which specializes in looking at the movements of stars. Webb, you can do almost anything, and that is why it is so popular in our community. Almost all astronomers who are interested in doing observations can use it. So we can break down its targets and its science missions in 4 broad categories. The first of which is alien worlds. So it can look at worlds within our own solar system. The only caveat to that, however, is that it can never look inwards from its orbit. So because it's an infrared telescope, it's very sensitive to heat and radiation. It has a huge sun shield protecting its mirror and instruments from the sun, which means it must always have the sun shield between the sun and that mirror. So it can't look inwards towards the sun, Mercury, Venus, the Earth, and the moon. But everything outside of its orbit is fair game. So it has looked at different objects in our solar system, but we can also look at alien worlds beyond our solar system that we call exoplanets, and I'll go into some of that detail soon. We can also look at the life cycle of stars. So stars, we know, are born, they live a certain amount of time, they die, and depending on the type of star, they can have very different deaths. But the main key here is stars have very dusty lives. And the issue with dust is that it tends to block out light, but not infrared light. That's one of the magical powers of infrared light. You can actually see through gas and dust using infrared light. So we can probe into the life of stars and peek into secrets of their lives like never before with an infrared telescope like Webb. We can also study the evolution of galaxies all throughout the history of the universe. So galaxies evolve over billions of years, and they rarely evolve in an isolated way. I like to think of galaxies as very social creatures. They're often found in groups or clusters, like the Virgo cluster that I study. And in those groups, just like with humans and animals, they interact. And sometimes they fight and they tear each other apart and they collide and they merge. So we're interested in studying how galaxies have evolved over the history of the universe, all the way to the very, very early universe. And one of the main goals when the telescope was conceived of was to try and look as far back as possible, farther back than ever before in the early universe, only a few hundreds of million years after the Big Bang. And we have been able to do that already in just over a year of observation. So that's been exciting. So I'll go through some of the key discoveries, but this is only a small sample of that. I'll give you the link if you want to find out more. If you have a favorite discovery that I didn't mention here, it's because I could talk for hours and days really about all the discoveries Webb has made. So I had to make a selection at some point. So starting close to home, inside of our own solar system, these are 2 separate pictures. On the left, you have the picture of Neptune and 7 of its 14 moons. You can see it's a wider shot. You can see 6 of its minor moons that are closer in there. You can see the rings of Neptune and Triton, which is its largest moon. And you can actually see that in the infrared, Triton is quite a bit brighter than Neptune itself. And that's because the atmosphere of Neptune lots of gas like methane, is absorbing a lot of that infrared light. So you can see that because of the kind of light that you're looking at, it's not necessarily going to have the same brightness that you might expect in visible light. If you're looking at the right side here, you have Uranus. A closer in shot, you can clearly see Uranus's beautiful rings. You can see that Uranus is on its side. As we know, we think it was knocked over by an asteroid, and it's now rotating on itself in the other direction, vertically rather than horizontally, like all the other planets. But what I love about these pictures and all of the exciting observing programs for these two planets is that, to me, Neptune and Uranus are sort of like the forgotten siblings of the solar system. They have never had a dedicated probe mission visit them. Even Pluto, which is a dwarf planet, has had New Horizons. So the best pictures that we have of Neptune and Uranus are from Voyager flybys in the 80s. So these pictures taken by Webb are actually the best pictures and the best data of these two planets in 30 years. And in those 30 years, lots have changed inside of the atmospheres of these planets. So people specializing in solar system objects and solar system planets have lots and lots to understand with all the changes they're seeing in these pictures. We have Saturn, which is, of course, very well known for its rings. So you can see the rings are quite bright here in the infrared, brighter than the planet itself. You can see faintly some of its moons here. And I want to focus in on one moon specifically, Enceladus. So Enceladus is probably my favorite object in the solar system. It's what we call an ice moon. And so it's covered by this thick crust of ice with a liquid ocean underneath. And it's actually possible to get a hint of what is in that liquid ocean because there are what we call cryovolcanoes at the surface of Enceladus. So these cryovolcanoes are ejecting liquid water from that liquid ocean underneath. And you can see plumes of water coming off of the surface of Enceladus here. And we've had the Cassini probe, for example, pass through those plumes of water and sort of sniff to figure out the composition of that liquid ocean. But from farther away, the Webb telescope can use its tools to look at light shining through those plumes of water, also to understand the composition. And so if you ask me where the most likely place to find alien life would be, at least in our solar system, I would not tell you Mars. I would bet that it would be on one of these ice moons like Enceladus and Europa. So we have this observation here of one of the plumes coming off of Enceladus right here. You can see the plume quite a bit larger than the moon itself. And you can see a figure that shows a spectrum that was taken by Webb of the light going through there. And we were able to determine the presence of molecules that don't indicate that there's life, but indicate that there's potentially an environment that could benefit the development of life before or in the future. So they remain very, very interesting targets for the search for extraterrestrial life. Now, if you go further out into the universe beyond our solar system, we go into exoplanets, these worlds that are orbiting stars other than our sun. But of course, they're so distant, we can't take nice pictures of them. So we have to be very clever. And luckily, I am surrounded by very clever people at the Trottier Institute for Research on Exoplanets. We're now about 65 members across 5 different institutions or universities in Quebec, mostly at the University of Montreal. And these are people that build instruments like the Canadian instrument on Webb and other instruments on ground-based observatories. They take data from these instruments, they discover exoplanets, and they understand how these exoplanets were formed, how they evolved, what they're made of, in the hope of finding alien life. So one of the ways that we detect exoplanets is called the transit method. So of course, they're so far away, it's hard to get a direct signal from the exoplanet or direct image. Instead, what people do is they try to see the indirect effect of an exoplanet on the star that it orbits. So here you can imagine fixing a number of stars in the sky with your telescope. You're staring at them, and you may notice once in a while that some of the stars will become periodically dimmer or less bright. So we can imagine what happens in that instance is that a star will be blocked partially by a planet orbiting around it and transiting over it. So it's sort of akin to an eclipse or an occultation. It's a body moving in front of another body. And depending on how deep that dip is in the brightness, that can give you an indication of how large the object that blocked the light is. And if you keep staring at that star and you notice that the dimming of the light happens at a regular interval, that actually tells you the orbital period of the object going around the star. So just with that piece of information, you can tell that there's a planet that's about this big, that's orbiting at this speed around this star. So this is the sort of bread and butter of detecting exoplanets, the transit method. And the majority of exoplanets that we know of have been detected using this method. But once you've detected it, you want to know more. So this is where the Webb telescope swoops in and tries to get us more information. So what happens is when the planet passes in front of the star, of course, the rocky part or the solid part of the planet blocks out the light. But looking around us, we see that the Earth's atmosphere is not completely opaque. It's actually translucent or even transparent. And the same thing goes for a lot of these exoplanet atmospheres. So when light passes through the atmosphere of these exoplanets, we can actually capture that light, and the light will be affected by the atmosphere that it passed through. So depending on the molecules and the atoms found in the atmosphere that the starlight passes through, it will leave a fingerprint or sort of like a barcode in the rainbow spectrum of the star. And it'll show up as these black lines. These black lines will give us a code, a cheat code, as to what the composition of the atmosphere of these planets are from tens or hundreds of light years away. So it's really quite remarkable. And the Webb telescope is the best tool in the world or in the solar system to do that at this moment. It's been really, really breathtaking, the quality of the data that we received. So one of the first planets that this was performed on was WASP 39b. It is a hot Jupiter type planet, 700 light years away. So we know it's large, about the size of Jupiter, but very, very close to its star. It only takes 4 days for it to orbit around its star versus Mercury, which takes 88 days to go around the sun. Very hot, 900 degrees Celsius, so not a good candidate for alien life. But because it's so hot, its atmosphere has been puffed up. So it is a very, very good trial target to test the Webb telescope and make sure all of those techniques we're hoping will work actually work. It's a good target for that. So summer of 2022, observations were taken by an international team, including many of my colleagues at the University of Montreal, led by Professor Bjorn Benneke and many of his students. And they discovered the most detailed menu of molecules and atoms in an exoplanet atmosphere ever detected. So many instruments were used for this, including the Canadian instrument nearest right here. And some of the molecules detected includes water vapor. I emphasize vapor, not liquid water. Unfortunately, it's too warm for that. Carbon monoxide, sulfur dioxide, and this was the first time we've ever detected carbon dioxide, so CO2, what we breathe out, beyond our solar system. So this was a huge first. And CO2 alone, we know, is not a sure marker for alien life. There's lots of CO2 on Mars, for example, but no signs of alien life yet. But it can be a part of biological processes. So it's very, very crucial that we know that we can detect molecules at this level of precision, like CO2. So as I mentioned, this is not a good target for alien life, but it was a great, successful first test to make sure that this technique of looking at the composition of an atmosphere works. But since then, the same technique has been used on smaller terrestrial, more Earth-like planets in the search of biomarkers or biosignatures signals that would be a better indication that there is organic life. And we've actually found a tentative biosignature on this world, K218b, which is an ocean world. So already it's more promising. It is smaller, a little bit bigger than the Earth, but smaller than a Jupiter-sized planet. We believe it may be covered by a thick layer of liquid water. It's in the habitable zone of its star, which means that the temperature there is right for water to exist in its liquid form. And we performed the same kind of study where we looked at the light of the star passing through the atmosphere. And this is the spectrum that we found. So again, carbon dioxide, methane was detected, but one very exciting molecule was dimethyl sulfide, or DMS. Now, DMS on Earth can only be created by organic life. That doesn't mean that this is for sure created by life elsewhere in the universe. It just means that if this signal is real, we don't currently have any other explanation for how it was created. So that's why I say it's tentative. That's how science works. Ideally, we will get more data to solidify the signal. And if it's still there, then we have to start finding explanations for its presence. Are there other ways that dimethyl sulfide can be created? Or is this maybe a sign of alien life? So stay tuned. There's still lots for us to discover on this exciting world. Going to stars now. I mentioned stars are born, they live their lives, and then they die, different kinds of deaths. So stars are born in places that we call star-forming regions or stellar nurseries, such as the pillars of creation that you can see here. This is my favorite image that the Webb telescope has taken. And it's breathtaking and beautiful as it is, but the true power of this image for me is when you compare it with the same region observed by the Hubble telescope. So here you can see the power of using infrared light. In the visible light as seen by Hubble, you see lots of gas and dust that is blocking out stars in the background and stars within the pillars themselves. But because infrared light can see through that gas and dust, we're actually able to peek inside these dusty caverns to look at the first few moments of life in the life of a star, the first few millions of years as it's forming together. So that's really wonderful. And we never had that level of detail in the first few moments of a star's life. So that's beautiful. And this was an image that was released for the 1 year anniversary of the Webb telescope's first images in 2022. So it's another star forming region, Rho Ophiuchi, and you can also see lots of structure in the nebula, which is structure that we didn't have the resolution to see before the Webb telescope. So beautiful image here. You can also look at the birth of individual stars called protostars with the Webb telescope. Here you have one that is being created at the very center here, and the birth of stars can actually be quite explosive, where not all the material will neatly accumulate at the center. You'll have the creation of huge jets, polar jets that are exiting the poles of the star. So this is why you have this sort of hourglass shape here. Same thing in this Herbig-Haro object. You have these huge jets coming out. And the center, the sort of dark region, that is where not only the star, but potentially the protoplanetary disk where planets are being formed. So to give you a sense of scale, on the image on the left, if you see at the very center, there's a dark band that goes across here. That's about the scale of our solar system. So the jets are really, really massive in these systems here. And eventually, stars will die, and it will be once again a very gassy and dusty death. So for average stars at the end of their lives, they will puff up into red giants and blow out their exterior envelope into what we call a planetary nebula. So on the two opposite ends here, the southern ring and the ring, they are planetary nebulae. This is probably what the death of the sun will look like. And at the very center, you have the leftover white dwarf. But for larger stars, it will be a more explosive death. They will explode in a supernova. And at the very center, you may get a neutron star or possibly a black hole that's left over. And all the material that's been blown out will go into the interstellar medium and be eventually recycled and create new stars. At the end of a life of a star, as it's getting older, for massive stars, they become what we call Wolf-Rayet stars, where they're already blowing out lots and lots of gas and dust. So here you see the very bright star at the center, and it's getting old, it's getting cranky, it's blowing out all this dust. So about a year ago now, the Webb telescope observed one such star, and it was actually a Wolf-Rayet star in a binary system. And so these are two co-orbiting stars. And it was predicted that every time the stars came close to each other, the Wolf-Rayet star would get particularly agitated and blow out even more gas and dust. But we've never had the spatial resolution to really see if that might happen until we had the Webb telescope. So we pointed the Webb telescope towards this object, and lo and behold, this is the image that we saw. And it really blew everyone away because of what it looked like, but also because of how well it matched the scientists' computer simulations. And what you're actually seeing here is every time the two stars have their close passage, every 9 years, you have that big shell of gas and dust expelled by the Wolf-Rayet that is visible here. So it's sort of like counting back the rings in a tree trunk. You're counting back the age of the system. Every ring is equal to 9 years. So you can actually study the reverberations of the co-orbiting stars. And you can study the gas itself, which will eventually turn into new stars elsewhere in the universe. You can also study galaxies with the telescope. I mentioned that galaxies are very social creatures. They interact with each other. On the left, you have the Cartwheel galaxy, which is a very rare ring galaxy because of a smaller galaxy, this one on the left, passing through it recently. It's ignited a ring of star formation around the galaxy. And on the right, you have VV191, who are two interacting and colliding galaxies, which will eventually fuse and merge and form one larger galaxy. This is one of the first images that was released by the telescope. Stephan's quintet, you have 5 galaxies, 4 of which are physically close to each other. The other one is farther away, but it seems close because of projection. And you have these 4 here that are interacting with each other, and these 2 are very close to fusing together, and this one up top is crashing into the duo there. And what's happening because of that is you have these shock waves of gas as they're colliding together. This is pushing gas together and causing the birth of new stars. So these orange fireworks are new stars being formed because of the gas pushing together. But if you love galaxies and you want even more of them, this is the image for you. This is the Webb Deep Field of Galaxies, which contains 7,000 galaxies in a very small region of the sky. And there are some galaxies that are closer to us, some that are farther away. The ones that are closest are larger. They appear more white. They're about 4 billion light years away. But the ones in the background, all those Christmas lights, those are the ones that are the treasure trove for astronomers trying to find the furthest, most distant galaxies away. So one of the other powers of infrared light is that it allows you to see these very, very distant galaxies. So looking at the same part of the sky with Hubble and with Webb, you'll notice that there's a lot more action going on in the background of Webb. And yes, that's in part because Webb is a larger telescope, more powerful, but it's also because of a phenomenon called redshift. So these galaxies are actually emitting visible light, actually quite blue, even ultraviolet light. But because the universe is expanding, as these galaxies are moving away from us, their blue light is being stretched out and redshifted into a red color and even into infrared light. So actually, from our point of view, the only way to observe the most distant galaxies from us is to look at infrared light. If you also take a closer look, you'll notice that some of the galaxies look a little bit weird. They're kind of stretched out like noodles and strangely deformed. And this is because of a phenomenon called gravitational lensing. So those foreground galaxies, the larger white ones that I mentioned, they are so heavy that they're warping the light. So they're acting sort of like a magnifying glass that is warping and deforming the light of the distant galaxies behind. And sometimes you can get weird phenomena where the background galaxies is deformed into almost a perfect ring like that. It's a little bit annoying because your galaxy looks weirdly shaped, but it can actually magnify and make that galaxy brighter by up to a factor of 100 times, which allows you to see things that would otherwise be too faint to see. How do we know that these galaxies are very distant? How do we know that sometimes even these galaxies can have double images of themselves, but we're looking at the same galaxy? It's all through spectroscopy. So the same way that exoplanet atmospheres have fingerprints for their elements, for their composition, galaxies have their own fingerprints as well. So if you take a spectrum of a galaxy, like this one, using the nearest instrument, you're looking at these two galaxies here, you're comparing their fingerprints, and you can see they have the same fingerprint. And the fingerprint also tells you how far it is. So this is how you can determine that these two are actually two double images of the same distant galaxy that you are studying. So this particular galaxy was actually not only doubly imaged, but we found a third image of it. It's a triply imaged galaxy that we nicknamed the Sparkler. And it's called the Sparkler because it has all these little sparkles all around it. So a Canadian team took a closer look, studied these sparkles, and determined that they were globular clusters, so beautiful objects for astronomers to photograph. And not only were they globular clusters, but they seem to be the oldest globular clusters ever detected. So that's also very, very exciting that Canada, using Canadian astronomers using the Canadian instrument, were able to make this discovery here. So here, yes, they're looking at photometry of these globular clusters to identify their age. So they're very, very old. Finally, I mentioned that everyone is sort of racing to try to find the earliest galaxy. So it's sort of like this redshift far frontier that everyone is trying to reach. Redshift is that phenomenon where light is being shifted from blue to red, and the higher the redshift, the more distant the galaxy is. So everyone is pushing how far back we can see using Webb, and some of the galaxies that have been identified with Webb were present when the universe was only about 2% of its current age. And this beats the Hubble Space Telescope's record in only a few months of usage of Webb. So that was really, really wonderful. So like I said, this is just a small sample of all the wonderful things the Space Telescope, the Webb Space Telescope, has been able to do in just about 14 months of science, and there's still many, many years to come. So if you're interested, I invite you to go online at webtelescope.org. It's the official website of the Space Telescope Science Institute, which runs all of the telescope operations and the imaging for all of the beautiful discoveries that we're doing. So thank you so much for your attention, and I'm happy to take your questions.
So thank you very much, Nathalie. You can hear me okay?
Yep.
Okay, super. So if you have a question here, I've got a walk around mic so the folks online and Nathalie can hear you. So I've got 2 questions online. Any questions in the audience here? Just put your, I can't see very well. I got the light. Carl's gonna have to. Okay, it's on.
Nathalie, you described the transit method for finding exoplanets. For those stars whose planetary orbits are not oriented in the right plane, you wouldn't have these transits. And is the instrument on Webb sensitive enough that you would be able to detect some movement of the star due to gravitational forces if there was a very large exoplanet? Thank you.
So that's an excellent question. And what you've just described is actually the radial velocity method of detection of exoplanets. So there are dedicated instruments, mostly on the ground, which look for that sort of wobble in stars that is caused by the gravitational pull of planets. And we have instruments that can actually detect that wobble of Earth-size exoplanets, more around smaller stars. So it's like a smaller star for you to sort of shake around. But members of IREX have actually built 2 of these machines, one called Spiru, which is on the Canada-France-Hawaii telescope, and it's been there since 2018. And the other one is called the Near Infrared Planet Searcher, which we've just commissioned in Chile just a few months ago. And so, yeah, usually what happens is that we detect exoplanets using this radial velocity method with these specialized instruments, and then we try to get time on the Webb telescope to get further observations.
Okay, so we got a couple of questions online. Robert Martin has 2 questions about Uranus, and he says, just curious whether Uranus moons and rings orbit roughly in the same direction as its rotational axis.
So the rings, they are also vertically, that's right. The moons, though, haven't been affected. So they're still in the plane of the solar system, I believe.
Okay. And talking about Uranus's North Pole, I heard it may have been knocked over, but must have been a long time ago. It's not a recent event.
That's right.
Okay. Why do some, this is from Malcolm, why do some stars exhibit diffraction spikes?
Yeah, so let me find a good picture that can show that. Oh, I just stopped my screen sharing, but maybe I can get it back quickly. Can people on in the room still see my screen?
Yep, absolutely.
Okay. Okay, I'll use this one here, so hopefully you don't get a lot of close-ups, but you see a lot of stars in the background there. So essentially what happens here is these stars are more in the foreground, they're closer to us, and so they're much, much brighter. And usually what happens there is you will have interactions in the optics of a telescope. And it's very, very interesting, actually, because the diffraction spikes of the Webb telescope, you have 6 big spikes and you have 2 small spikes inside. And that is a different pattern, different diffraction pattern than the Hubble Space Telescope, which just has 2 big spikes like that, or like 1 big X. And that's because of the shape of the telescope. So based on the shape of the mirror, you will have a different diffraction spike. And sort of every telescope has its own little signature. So this is a fun party trick that I always propose to people. If you want to impress people based on who you're hanging out with and you're looking at a picture, you can tell if it is a Hubble picture or a Webb picture based on the diffraction pattern of the stars. But yeah, it's an artifact for very, very bright objects that are sort of oversaturating because it's interacting with the optics of the telescope.
Okay, thank you. And then just a comment from Anne. Not a question, but praise for your ability to convey intense material to an astronomy newbie. So that's great. Thank you.
Thank you so much.
So I don't see any more questions. So I just like to thank, I'm sorry. Yes, Simon has a question.
That was a wonderful tour de force. Your field is galaxies, and as I understand it, when Webb started peering as deeply as it could, it began discovering things about galaxies that surprised some people. I know it's a deep, deep topic, and you've only got a minute or 2, but can you give us a quick overview of where things are at with the surprise galaxies?
Yeah, thank you for giving me the opportunity to talk about this. So it's a long-standing issue with galaxy studies. The further back we look, the more we expect galaxies to sort of fall on the growth line that we expect based on the laws of physics and the constants of the universe. It's sort of like you think of a human, you have a certain growth pattern for a kid that you expect, and you're always hoping your kid is like not too far from that line. And before the Webb telescope, you were very much looking at an epoch, an era of the universe called cosmic noon. It's about halfway through the history of the universe. And it's when telescopes were the most actively forming stars and growing and accumulating mass. But even then, we saw galaxies that were too large. We didn't understand how they could have accrued so much mass in only 6 billion years. It didn't really make sense. So we thought to ourselves, okay, we're going to solve this. If we look further back into the childhood of these galaxies, maybe we'll see what the sort of crux was, which kind of part of its growth history is sort of the outlying mystery of why they got so big. And so we figured, okay, we're going to look back to where they were basically created or formed, and we'll see if that matches what we expect. And the issue is they're still too big there. So it's as if we went to a nursery and we were expecting to see a bunch of babies, but we found a bunch of teenagers instead. The galaxies found are too large. They have too much structure. They're already starting to have spiral arms, which is way sooner than we would have expected. And they have too many stars. So we don't understand how they got so big right after they were born. So we think either there's something we don't understand about galaxy evolution, or the laws of galaxy evolution, or perhaps they started forming earlier in the universe than we thought. There's also sort of like a nuclear option, which some people have suggested, but most of the community is not there, is that the age of the universe is wrong. And the universe is actually older than we think, but we have a lot of evidence pointing to the age of the universe as we know it being correct, more or less. So I'm not there, and most astronomers are not there yet.
Okay, thank you. Yep.
Hi, Nathalie. That was an awesome presentation. Quick question for you. Given the Webb's telescope ability to look in the infrared, there's going to be there's obviously a technical bottom limit to the wavelength that it can see. Theoretically, what does that translate to in terms of seeing something from time zero? Like how far from time zero could Webb theoretically image something, given its redshift?
Yeah. So luckily, from time zero, there wasn't a whole lot that we could see. There was a certain time before which the universe was just like a huge opaque wall, and it's just impossible to see. So we can't even look. We don't even have to worry about time zero. We can worry about something that's a little bit more attainable. In general, the issue isn't necessarily that there won't be any light converted to the infrared through redshift. It's just that every object has a peak light or a peak wavelength where it is easier to see. And I would have to do the calculation. I've never done the calculation myself. The highest redshift that we can, the longest wavelength that Webb can look at is about 30 microns. So I've never done the calculation myself. I should maybe give it a try. But technically, we should be able to see galaxies only a few hundreds of millions of years after the Big Bang, within that range that is still accessible. But I'm not sure at what point the visible light would no longer be accessible in the mid-infrared.
Well, thank you very much, Nathalie. That's a fascinating presentation. We really appreciate you spending time with us here this evening. And maybe a year or two from now, we'll have a follow-up, because it seems like every few weeks or so, there's a new image from the James Webb Telescope.
Absolutely.
Okay, well, thanks again, and thank you.
Thank you. Have a nice weekend, everyone.
Okay, so we're going to take a bio break. So a couple of things, come up and see me. I have your tickets for the door prize. Oscar is at the table. He's selling dinners to our buffet dinner meeting. And also we have some DVDs that were created on the history of the Ottawa Centre Observatory. And they're available on the table there. So this table is door prize only. Take a look, see what's there. Table over there, help yourself. And we're going to have a 10-minute break. Reminder that the museum is closed right now. And we do have a trivia challenge. Do you bring that up? There we go. Apart from Pluto, what are the 4 other most recognized dwarf planets? And what year did Pluto become reclassified as a dwarf planet? So I'll get the lights up a little more, please. Okay, so let's see how we did on the trivia challenge. Apart from Pluto, what are the 4 other most recognized dwarf planets? And what year did Pluto become demoted to a dwarf planet? The next slide, please. Ceres, Eris, Makey, and Haumea were the other 4. And 2006 is when Pluto got demoted. So I believe Oscar is up next. Let me just move the slides forward and see. Yes. He's coming. While we're waiting for Oscar, those who are doing observations, the observation order is Richard Taylor, Jim Thompson, Jim Sophia, Andrea Girones, and Paul Cloninger. Okay, so just keep that in mind. I'll remind you as we go into those presentations. There's your remote. There's forward, back, and there's your green laser.
Okay. All right. There we go. All right, so I'm gonna do just a bit of a, I don't know if you call it a product review or a little bit of a walkthrough of an interesting piece of equipment I ran into maybe about a year ago, called the OCAL electronic collimator. So maybe I'll start talking a little bit about what collimation is for those who aren't familiar, but it's really just the process of aligning all of the reflecting telescopes optical elements so that they're all concentric and aligned with each other, so such that you can get the best image or view out of the telescope. There we go. So what's involved? Generally, the first step of collimation is to adjust your primary mirror, and I'm talking strictly a Newtonian here. There's obviously other methods for Schmidt-Cassegrains and Ritchie-Chrétiens, etc. But this is just Newtonian telescopes. So you would fiddle with the collimation screws on the back of your primary cell to tilt your primary mirror in one orientation or another. And then your next step is to adjust the collimation or the tilt screws on your secondary mirror. So these 3 guys here let you tilt the mirror in certain orientations, and loosening and tightening this bolt will move the secondary mirror either further in or further up from the relative to the tube. And then your third step is you go back to the primary mirror and sort of realign the primary mirror to whatever movements you made in the secondary. So what options are available for doing collimation? These are some popular items available out there. There's a bar-load laser, and I've got some of these items here, so maybe if people are interested, they can come look at them later. So this is a bar-load laser. The idea is you shine a laser through a Barlow lens, and it, I don't know, it's hard to demonstrate, but it kind of creates a certain pattern, and if it was pointed into a telescope, it would create sort of this pattern on that white face. And what you're trying to do with this particular tool is to align your primary mirror. You want to get the shadow of the donut on your primary mirror be concentric with the bore through the instrument. Another option is a Cheshire eyepiece, which I've also got here. And this just gives you a really narrow view of down the axis of the telescope. And the very narrow aperture, it's obviously difficult to see from here, but this has got a bit of a pinhole about, I don't know, not much thicker than the tip of a ballpoint pen. So that controls your field of view into the axis of your telescope so that you can sort of eyeball the alignment of the elements. And then a simpler version of a Cheshire eyepiece is the collimating cap there, which just doesn't have any of the other components of the Cheshire eyepiece, but it has that sort of narrow aperture. Yeah, so the OCAL, so another option now is this is the OCAL electronic collimator. So it's made specifically for Newtonian scopes. Really, it's just a fancy camera, more than anything else that is able to actually focus on the elements of your telescope rather than having the telescope focus light into it. You do need a Windows PC to operate it, but it threads onto a standard focus tube using an M42 by 0.78 thread or a T thread, and it comes with an app that provides some visual aids for aligning all the components of the telescope itself. So I'm going to maybe take a few steps through how it works. So once you've got the collimator hooked up to your telescope and to a computer, this is kind of the view that you would get through the camera on the computer, which I think I've got all the components labeled out in a different slide, but maybe I'll just walk through them here. So this is kind of like the edge of the bottom of your focusing tube. This is the secondary mirror here. That's the edge of the secondary, so the edge of the face of the secondary mirror, and then the white disc is actually the edge of or rather the image of the primary mirror in the secondary mirror. So the objective of collimating here would be to get to basically get the entire face of this secondary mirror to be perfectly circular. So it's presenting a full circle, and you do that by adjusting the tilt and rotation of your secondary, and then making sure that it's concentric with the opening of the focus tube. And to do that, you may need to move the secondary up and down, and then also you want to get the image of the primary to be concentric with the face of the secondary. Let's see here. My button's not working, I think. Can you advance the slide, Chris, maybe? Woo, okay, there we go, fancy. See, I did this, but I forgot that I had. So I'll let the computer walk you through all the fancy components here again. I even did little handy arrows. So in the case when you're using the OCAL collimator, you can actually see the sensor of the collimator itself, and one of the final objectives to make sure that you've got it nicely collimated is that sensor should appear right in the middle of that image. So once you're using the app, you kind of get these tools which let you draw these fancy circles so that you can better visualize the alignment of the telescope. As you can see, my particular telescope here is really badly out of collimation. Unfortunately, I haven't had the time to collimate it. But the idea there is I would follow the steps that I talked about earlier. I would start by adjusting the primary mirror so that it appears to be concentric within so that when I align the blue circle with the image of the primary mirror, it's concentric with that red circle. And then I would adjust the tilt and rotation of the secondary to get it to be A, perfectly circular, and B, concentric with the green circle, which is the the edge of the focuser tube. And then lastly, I would go back and adjust the primary mirror so that it if it fell out of alignment when I moved the secondary around, so that I get it back into perfect alignment. Oh, there we go. All right, I guess I described the issues with the collimation there. Yeah, so the secondary is not concentric with the focus tube. Primary is not concentric with the secondary, and and at least to my eyes, it looks like maybe the tilt or rotation is wrong in the secondary, and it's a little bit out of round, or it appears a little bit out of round. So how does it stack up versus the other methods of collimating? It's nice because you get real-time feedback of the adjustments that you're doing. You can kind of, as you're turning the screws on the various mirrors on your computer display, you can see exactly what effect each adjustment is having on the scope. Whereas if you're using something like a Cheshire eyepiece, you eyeball it, you go to the bottom of the scope, you make an adjustment, then you have to come back to the eyepiece to see what effect that had. So you don't get to see the adjustment happen in real time. So it's makes it a little bit more difficult to sort of visualize what each adjustment is doing. The visual aids that the software lets you overlay on top of the image make it a little bit easier to detect errors in your collimation. So, something I personally find challenging is determining whether or not my secondary is truly presenting a perfect circle or not. So whether the rotation or tilt of my secondary is good, but when you have a nicely drawn circle on the computer, you can really try to pin it down really well. And the other thing is that the observing position is fixed. Whereas with your eye, if you're looking through here, there's slight effects of perspective if you shift your eye a little bit relative to the rest of the system. But when using something like this, the perspective is fixed, and it's true to the optical axis of the scope. And OCAL also claims that this device can be used with Schmidt-Cassegrains and Ritchie-Chrétiens and really any reflecting scope, but I don't know, because I don't know. I haven't tried it with my Schmidt-Cassegrains, and I don't own an RC. But some folks online have had luck using it. The cost though is a little bit prohibitive, I suppose. It's about $330 on Amazon for one of these guys, whereas a nice set with a Barlow, a laser pointer and a Barlow for it is about $250, and a Cheshire eyepiece is just like $50. That's about it. Anyone have any questions or anything? Yes. Yes. Yep. Yeah. Yeah. Yes. Yeah. Yeah, so I know that software because I've used it, and that's generally used for an out of focus star. So you draw the same overlay circles over the donut and the outline of an out of focus star. And I don't know exactly how effective of a collimation method that is for a Schmidt-Cassegrain. I think the truest test of a collimation in a SCT is with an in focus star and looking at the airy disk of the image of a star. As for a Newtonian, I think that you could probably use something like that to get pretty close. Where it might miss is in the in getting the precise tilt of your secondary, which you can fairly easily do with a laser pointer, I suppose. But yeah, I mean, I suppose it's a convenience thing, and whether someone's willing to pay for the convenience and the presumed precision. I don't remember what it's called. Sorry, what was that? Al's collimation tool. Yes, that sounds familiar to me. But yeah, I can after the meeting, I'll have these things at the table. People can look at them if they wish. If no one has any other questions. Oh, yes, I'll start over here. No. And the question over there? Yes. Okay, yeah, so what Andrea is saying is that she owns one of them as well and has used it with her Schmidt-Cassegrain, has had good results, and can be used during the day. Yes. And that is also, I mean, using it during the day is also true of a bar load laser and a laser pointer as well as a Cheshire eyepiece. But yeah. Yeah, I think I've seen that video by Queeve as well, and he did seem to get it pretty close. Okay, anything else? No, okay, thanks very much.
Okay, we're going to move into our observations, and we have one remote, which is Richard, and he's up first. So Richard, you can just call out to Chris to change the slides. There we go.
Okay. So you may remember last month I showed some of my observations that I had taken at the North Frontenac site. I have a rental cottage nearby, so it's really wonderful to get the nice dark views of the southern sky. And so tonight's pictures are some of the highlights of the southern Milky Way. Here's the Lagoon Nebula, M8, and this nebula always seems to reward getting more images of. And this is a stack of 11 200-second exposures with the M100 Canon camera. So it has a nice wide field of view. I was deliberately trying to exclude the Trifid Nebula, and I did catch the starfish cluster, NGC 6544, in the lower left. And I was surprised to also find a set of nebulosity NGC 6599 in the upper left, but the Trifid Nebula photobombed the top right corner as well. Using PixInsight and the Blur Exterminator tool, I managed to get a lot of detail in the dark nebulas inside the lagoon. So you've got the star cluster of new stars that have just formed. You've got the wispy nebula all around it, and then you've got the dark dust clouds coming across it. So I was very pleased with this view. Next one, please. Now, we were seeing a few pictures of this from the James Webb and from the Hubble. This is the Eagle Nebula, M16, with those pillars of creation right in the middle. So just those little dark lanes of dust, those are the places where new stars are being formed. Thank you. Now, this was taken with my ASI 178 MC camera, which is a dedicated astro camera, so it has a much better, picks up the red end of the spectrum much better than the Canon camera does. Next one. And this is the West Vale Nebula, or the Witch's Broom Nebula. I keep coming back to this one because it's got a lovely amount of detail in the wispy features. This is a supernova remnant from quite a long time ago. It's a huge structure altogether. The Vale Nebula is in one of the wings of Cygnus the Swan, and I find it's too large for any of my cameras to capture as a whole. This is a close-up view of just one side of the nebula with the ASI 178 camera. And it's really wonderful also for the colors, because you've got the bluey green colors from oxygen, I believe, and then you've also got some red features as well, which I presume is hydrogen. Now, the other interesting thing of this kind of view is that I think there must also be some dark nebula that we can't actually see in the picture. But you'll notice that in the lower half of the image, there's a lot more of the Milky Way stars than in the upper part of the image. So it looks almost like the Veil Nebula here is like a net catching the stars. But as I say, I think what it really is that there's probably more nebulosity that just has no light of its own, and it's blocking some of the light from the stars behind it. Next one, please. I haven't had many opportunities to do observing since I got back from the college, but I did have a lovely night on October the, what was it, 16th. Nice warm night and very, very clear. And so I decided to try a project I've been meaning to for a while, which is taking a mosaic of pictures across the Andromeda galaxy. Once again, the Andromeda galaxy is a huge structure in the sky. It's much bigger than the full moon. And so it just barely fits into the field of view of my Canon camera. But I wanted to use the better facilities from the ASI 178 camera. So I took a 6-panel mosaic. Quite a tricky thing to do because the Andromeda galaxy is not lined up north-south or east-west. It's at an angle across the sky. So you have to move it in both right ascension and declination to step across the galaxy to get the panels of the mosaic. So quite a challenge to get the original pictures. I was trying to do it all in one evening, so I only took half an hour for each panel. And then just about the time when the clouds were coming in, I was hitting the time when I'd have to flip the mount over the meridian. So I said, that's enough for tonight. And then I spent 2 days afterwards piecing together this mosaic and processing it. I'm quite happy with the results. The stars are nice and sharp and tiny. You got lots of detail in the dust lanes, but I did have some problems trying to separate the outer wisps of the galaxy from the Ottawa light pollution, because this was just from my backyard and inside the city. So obviously more work to be done. Go out to FLO or go out to North Frontenac again and see if I can get a better picture from darker skies. Thank you. That's all for me.
Okay, thank you, Richard. Jim Thompson, followed by Jim Sophia, Andrea, and Paul. Good luck.
Does the clicker work?
Sometimes you got to point it at Chris.
Which is basically telling him to advance the slide for you.
Well, no, it works sometimes.
Okay.
If it doesn't work, turn on the green laser. Get us attention.
All right. It's great to be back, everyone, to see all your shining faces. A few more gray hairs than I remember when last we met. So my first couple of images are of the observing challenges for this month. The first is the lunar challenge, which is the 56-kilometer crater Franklin. I had to go kind of back into my catalog of past observations to find a favorable lighting, a favorable phase for the moon to really get a good view of the crater. This picture on the left was taken back in February of 2022, but the Terminator was well placed to show how complex looking a crater it actually is. There's clear evidence of an apron of impact melt around the perimeter. You can see that it has terraced walls. There's a flooded floor and a clear central peak. So it's actually quite an interesting crater when you look at it in detail. The image on the right is from a more recent observing session, one of the very few observing sessions that I was able to manage this fall. I don't know about you, but it seemed like it was cloudy every time that you had free time to do some observing. So this is one of the few opportunities I had to do any lunar imaging this fall. But you can clearly see the floor of Franklin crater, which I've marked with the red dashes. It's dark in comparison to the surrounding material, which would indicate that it has been the floor has been flooded later in the life of the crater with basalt lava. And if you look very carefully at the image, you can see that there's actually two different shades of dark gray, implying that there may have even have been two events of flooding. And that is also evidence from looking at the large sea of tranquility in the lower left, where you can see two clear shades of gray, indicating that there are two different events, basalt lava of two different chemical makeups, resulting in the different shades of gray. Anyway, interesting crater. And we can move on to the next slide. Oh, great, thanks. So this is an image of the Advanced Observing Challenge for October. It's not a very good picture. If you look right in the middle, there's a fuzzy star, and that is NGC 1275, the main galaxy in the Perseus A galaxy cluster. I looked through all of my observing files all the way back to find an example of observing this object, and I had to go all the way back to when I actually started with electronically assisted astronomy. This image is from December 2011, and I was using the first camera I ever used for astronomy, a Melancam Extreme. It was taken from my backyard and is a stack of 4 60-second frames. Not very impressive looking at it. If I didn't tell you that there were galaxies in this picture, you would have never guessed that to be the case. But if we go to the next frame, there's actually a lot of galaxies in this image. Every one of those green circles is a galaxy. So this has kind of reawakened my interest in this area. This part of the sky is quite prominently placed high up in the beginning of the evening. So if we ever get a clear night, I might make another attempt at this using the tools that I now have available 12 years later. An example of which, of what can be achieved now, is my next image. This is of the Eastern Veil Nebula, so the other side of the veil structure from what Richard showed just before me. This was taken from my backyard, where the Bortle scale is 9+. I can see about a half a dozen stars on any good night. But the technology has evolved to a point where seeing something like this from your backyard in a matter of minutes is very, very achievable. So this was taken with a 4-inch refractor and an ASI 533 MC Pro camera with an Optolong L Ultimate filter. It's a 3 nanometer wide passband dual band filter, which is really part of the secret sauce that allows this to be done from my backyard in central Ottawa. It's a live stack, so no processing. This is what I saw on the screen, live stack of 28 30-second frames. The particular object is about 2,400 light years away. As Richard mentioned, it's in Cygnus, and scientists don't have a clear idea of when it occurred, when the supernova occurred, but it's around 10 to 20,000 years ago. Next image, please. Oh, sorry, that was from September 22nd, so actually just a couple months ago. On the same evening, this is another image from that same session. I included this image tonight in the theme of Halloween for all the kiddies out there. This is IC63, the Ghost Nebula. It's a combination of emission and reflection nebula about 550 light years away, so pretty close by, in the constellation Cassiopeia. The reflection part is not visible in my image because, again, I was using the L Ultimate filter, which blocks all of the blue part of the spectrum, so the reflection is not visible. It's the same setup as before, a 4-inch refractor, and it's a live stack of 31 30-second frames. My final image, thank you. This was captured at my cottage near Petawawa on the Quebec side of the Ottawa River on September 30th. This was late in the season, and we were shutting things down at the cottage, and we just happened to get a nice clear night. I believe I was online with Jim and Simon this night. Actually, we were zooming each other from across southern Ontario. So this is a tile of 2 images showing the central part of Cygnus. The head of the swan would be in the upper right, and the tail would be in the lower left. Each image is a live stack of 30-second frames with no processing, just some tweaks to the histogram for the dark and white points. I really love exploring the night sky with a wide field of view. You've probably heard me playing that horn a number of times in the past. But when you see such a wide variety of details and object types in the same frame, all in context with each other, it really, I don't know, helps me appreciate better what it is that I'm looking at. In particular, in this combination of 2 frames, some popular objects that you might be familiar with are visible. So in the lower left, the brightest nebula we see there is often referred to as the Butterfly Nebula. The bright star seen is Gamma Cygni. That's the star right in the middle of the cruciform shape of the swan. In the middle is the Crescent Nebula, NGC 6888. And then in the upper right is the Tulip Nebula, which is Sharpless SH2101, I think. I can't remember. So it's interesting to see objects that you would normally see isolated in their own image all together in context. These images were captured using a monochrome camera, my Malincam DS432M, and a 4.5 nanometer H-alpha filter. I was using a newly acquired classic SLR lens, so this is going way back, 135 millimeter focal length, f1.8 speed, so a nice fast lens. And this was all mounted on a newly acquired, super lightweight, super portable, quite jazzy mount that I bought in preparation for traveling to the 2024 eclipse. But you will learn more about that next month. Thank you.
Well, hello, everybody. I have an image here. This is M33. This was taken from downtown Ottawa, off my balcony, using a William Optics 81 millimeter refractor and a Malincam Skyraider camera. There's about 7 minutes of exposure time with frames live stacked and post-processed in Serial, Topaz Studio 2, and Raw Therapy. M33 is a constellation is a galaxy in the constellation Triangulum. It's approximately 2.7 million light years from Earth and can be seen with binoculars under a dark sky. And if you have really good vision, you could see it naked eye. Next one, please. Or do I use my clicker? Oh, there we go. So this is a disk shot of the sun. Notice the bright areas showing the active regions and filaments. Filaments are solar storms, and they occur over the disk, but most of the filaments are located in the upper right corner of the sun's disk. And I actually, and I have a close-up of that if you'll move on to the next one, please. Okay. Oh, okay. All right. So this is a close-up area that I was referring to. The solar images that I've presented were colored in Affinity Photo 2. but I use, when I'm imaging the sun, I use a monochrome camera. And the name of the camera is ZWO ASI 174M. And I have a monochrome image to show you next. There we go. Oh, it's quite big there. So this is a monochrome image of an active region showing the bright magnetized areas or plages, the sunspot in the center, and a filament that appears to wind its way through the center and outward to the left. And notice the pattern and direction of the magnetized field lines that border the active region. Thank you.
This has your name on it.
Okay, my name on it? Oh. Wow. So hi, I've never been here before. It's a very bright light. Thank you. So these are my images of Venus that I took in September on one of our few clear nights. As you know, this is about a month after inferior conjunction, so it's still a crescent, but I couldn't get at it much earlier than that. So this was taken about 4 to 5 a.m. with my Celestron C11 telescope and the 290 mm camera. What I was trying to do was to show the clouds on Venus, which apparently show up in the UV range. So on the image on the left is a false colored image created where I use an infrared for the red, I use green for the green, and I use UV to make an RGB image. So that's a IR green UV image. And you can see that there is a shading around the center. And I should have brought the UV image because you can actually see there is some darkness in that same area. And I think supposedly that's how you capture the clouds on Venus. And just to make sure, I did a normal LRGB image, which is just red, green, and blue. And you can still see a little hint of the yellow, which would come out through the blue. So that was my attempt at getting a crescent Venus this year. I had to move my whole telescope to a whole different part of the yard, so I don't think I'm going back to try again with Venus. So how do I move the screen forward? Great, thank you. So this was just a really pretty picture of the Milky Way when I was in New Mexico this past month to look at the annular eclipse. This is a single shot of 13 seconds. It is an astro-modified camera, I'll give you that, but it's 13 seconds, ISO 3200, and a new 15 millimeter lens that I have, which was f2.8. And so this is end of season Milky Way. Am I not talking?
Look this way rather than at the screen.
Oh.
Every time you turn, we can't hear you.
Oh, I'm sorry. I'm going to look at the screen. It looks much better on this screen, actually. Yeah, so single image, and the Milky Way is very upright. It's the end of season Milky Way, and you can see just how much more you see even in New Mexico. Next, please. All right, so this was my annular eclipse image. I tried to do a whole sequence that would also have a landscape in the picture. Any of you who have been reading Alan Dyer's book on how to shoot the eclipse know that it's nice to try to get a landscape in, but both this eclipse as well as the one in April occur pretty high in the sky. So trying to get a foreground in your image, a mountain is a perfect solution. So I ended up at the base of the Sandia Mountains in East Albuquerque. I took the foreground at dawn before the sun came up behind the mountain so that I didn't have to expose my camera to an unfiltered sun. I took like a whole bunch of sky. I did 3 rows for the sky and the foreground because you don't want to go home and not have enough sky to fill your image. I ended up picking a focal length that was about 32 millimeters on a crop sensor camera. That meant that to get the whole sequence in, I had to turn the camera twice during the eclipse. So I set alarms. And that allowed me to get a little bit bigger disc. It was on a fixed tripod, so you can see the rotation, the field rotation of the sun as it moves through. All of the sun images were taken with filter, and then I had to assemble it all in Photoshop. But I was quite pleased with how it turned out, because we were supposed to have terrible forecast all week, and then it turns out we only had a little bit of wispy cloud. Next. I also took full disk images with an H-alpha telescope. The reason I did H-alpha for this eclipse was because there, at no point do we lose the whole sun. If you had, you wouldn't use an H-alpha telescope for the total eclipse, because during totality, you'll see nothing. But during an annular eclipse, it works out well. Bailey's beads is a phenomenon where during the eclipse at what's called second contact, when the moon is just about to go to full annularity, and at third contact, when it's leaving, you can actually still see some of the sun shining through the mountains and valleys of the moon. So that's kind of neat. In reality, there happen to be some very well-placed solar prominences, which is, I think, actually what you're seeing here as the Bailey's beads. There were some little flary bits that were sticking out. But I was quite happy how these turned out. I brought my little 40mm scope to New Mexico. I had the 174 camera, which is not my favorite camera for that telescope, but it allowed me to get a full disc, which was important because I didn't want to have to do a mosaic of 300 frames for my time lapse, which you'll see next. I processed them inverted. So you're going to see a bunch of sunspots, but they're flipped. So instead of the active regions looking white like they did in Jim's photos, they're going to be black, and the sunspots themselves are going to be white. And these two images were taken from a sequence I did that started at around 9 a.m. I took 750 frames every 30 seconds for 3 hours. And the next slide is going to be the time lapse. And maybe if it works, you'll hear the lovely dramatic music that you know that I like. So could you go to the next slide, please? And hopefully if you press play, you'll be able to see, oh, here we go. I'm on here. The little prominences up at the top, and there's a big one on the side too. That's it. Thank you.
Ooh, yeah. Well, it's good to see everybody again. This has a very strange feeling of deja vu to me, to be back here after all this time. Nice to see that we can do this again, especially for those of you that watched last month's meeting. You'll know that I have intermittent internet issues, so nice to be able to talk to you in a normal voice. Anyway, I've got a few images here. Some of them were ones I was going to show last month. Didn't quite work out that way. The presentation I was going to give last month, I think Dave says maybe we can run that in January, and I'll be here for that. So one of the challenge objects from the previous month was the Messier 29 star cluster, which you see here. This is a relatively small but reasonably bright cluster that's just south of the Gamma Cygni in Cygnus. It's it was discovered by Charles Messier in 1764, and it has an apparent magnitude of about 7.1 plus 7.1. So you can actually see this if you know exactly where to look. You can actually see this in binoculars. Data from the Gaia satellite puts this the distance to this cluster at about 5,200 light years, give or take, and it appears to contain about 50 member stars. This was taken with my 11-inch Edge HD and ASI 294 MC Pro camera. You can see the whole field has a bit of a reddish tinge to it. This cluster is embedded in a lot of red nebulosity there, and as such, it actually attenuates some of the brightness of the stars that lie behind it, and gives the whole frame kind of a reddish hue to it. Next one, please. Oh, I forget. Now I can do that. All right. So this is a view of another challenging object from the previous month. This is galaxy NGC 7479. It's a barred spiral galaxy about 102 million light years from Earth, and it's in the constellation of Pegasus. It was discovered by William Herschel in 1784. It's quite small because it is fairly distant from our point of view, and it only measures about 4 by 3 arc minutes in size. It has an apparent magnitude of plus 11.6. This itself is an interesting galaxy. It's considered to be a Seyfert type galaxy, which means it's undergoing a lot of starburst activity, and you can see that. Actually, I can use the pointer here. I think maybe yes. Voila! You can see there's a lot of active star formation going on, not only in the nucleus but along the spiral arms there as well. And what we think is that that starburst activity was triggered by a minor merger of this galaxy, probably with one of its satellite galaxies, probably about 100 million years ago. Next one, please. So we didn't have the nice clear skies you did, Andrea, and those were awesome images, by the way. But we did, for some folks, and I know talking to folks in Ottawa too, it was really hit and miss, give and take. I'm out in the Lanark Islands, about 20 kilometers west of Almont. Same deal for me. It was mostly cloudy, but it started to break up a bit as the eclipse was in process, in progress. Never totally cleared, but there were thinnings of the clouds and some gaps, and that allowed me to take a few shots. I was hoping to do a sequence myself and a time lapse of it, but that wasn't going to happen when I was only getting a clear view every couple of minutes or so, or a partially clear view. This was taken about 12 minutes after the maximum extent of the eclipse in our area, and you can see some hints of sunspots there as well. This was taken with a 300 millimeter lens on a stationary tripod. I also had my 11-inch Edge HD running because I want to get a closer look and see if this works for me. Yes, it does. So this is with the 11-inch. It's because it has I was running it at f10, so the focal length is 2,800 millimeters. Doesn't quite accommodate the entire disc there, but this is the part that I was interested in. You can see again, obviously the clouds moving. Was that me doing that? No, that wasn't me. You can see the clouds moving through there, but what you can also see is that the major sunspot groups that were visible on the disk did make an appearance there. The other thing I really enjoyed about this, and I was actually kind of surprised given the turbulence of the atmosphere, is that if you look closely at this, you can see that edge is kind of rough on the rim, whereas it's quite smooth here. Andrea was mentioning about Bailey's beads, which is the light streaming through valleys between mountains on the moon, just as the moon and the sun converge. Oops, sorry about that. Here you can see, I thought initially this was just, you know, scintillation or blurring caused by the atmosphere, but I got a number of frames like this, and I saw those. So I saw that unevenness, the same pattern of that unevenness over multiple frames. So these are mountains in the North Polar region, and you're seeing them in silhouette. So these are the kinds of mountains and valleys that cause the Bailey's beads phenomenon when you get a total eclipse like that, either an annular, as Andrea saw, or hopefully the total that we're going to get in April. So this is a good practice for that eclipse. So let's see if I can get this to work. Yes. Yes. I don't think so. Yeah, I don't remember that on my image. So, but if you want it to be, I'll say yes. Hocus pocus, abracadabra, bang, bang, bang. Next slide, please. That was the ISS, I think. So, as I said, we didn't get phenomenally clear skies, but for a partial eclipse, the sun and the clouds actually made for some interesting light show views like this one, and every one was different. So every frame I shot, like Andrea, I shot about 600 or 700 frames over the two cameras, and yeah, it was interesting to see a bit of that light show. In case you're wondering, this was the filter that I used was an Orion glass solar filter on the 300 millimeter lens, and on the view with the 11-inch telescope, that was with just a beta film on that, and colorized yellow to boost the contrast of the sunspots. All right, so cross our fingers for April. Hopefully we'll get clearer skies than that, but we'll see. This is just a view of the moon I took. It was just a kind of a test shot. I was doing some tests with my 82 millimeter refractor. So actually one of my favorite phases of the moon, because the placement of the terminator on the moon cuts through some of the really cool looking terrain in the southern highlands, and really boosts the topography that you can see because of the shadow play there, especially around the South Polar region, which as you know from the talks Jim and I did about a year and a half or so ago, is one of my favorite regions to explore. Also, it's going to be hopefully the site of the very next lunar landing that may occur in the next year or two with the Artemis mission. So we'll cross our fingers. But it wasn't a super fine night, but I thought it was a nice shot just for the relief of the craters that we see there. All right. Oh yeah, 82 millimeter Apo refractor on that one with ASI 294 MC Pro. Next one, please. On a much clearer night, this is the Perseus double cluster. This is a lovely object to see because you can actually see this with your naked eye. You can see the two clusters here, side by each. They both have a magnitude of about plus 3.75. So under a reasonably dark sky, when it's nice and high in the sky, you can actually see this, and in a pair of binoculars, it makes a wonderful view, or a small telescope. This again was shot with an 82 millimeter Apo refractor, and the coloration is a little bit different here from what I processed, but these clusters are they're very loaded with very bright bluish white stars there, and in fact you can see, I think research I did, this has had some each of the clusters contains over 300 of these hot large blue stars. So very, very nice object in close to Cassiopeia, actually. All right, next one.
So I got two more slides to show you. And the reason this one is not a great picture. I was debating whether I should show this to you or not. But the reason I did is because this was taken with the 14-inch Schmidt Cassegrain out at FLO. It was a crappy night. The moon was up and there were thin clouds moving through, so a lot of noise in the image. But the nice thing about this image is I've been doing testing up on the 14-inch, trying to get it ready and fully operational. And this is a single 15-minute guided exposure. So the reason I'm showing this slide and the next one was just more eye candy taken on a much nicer night is that I'm making an announcement here that with the help of Chris Tarrant and Oscar Echeverri for their technical assistance and their backbreaking assistance, plus our test pilots, Richard Taylor and Andrew Brown and Tara Servarsky, I think I can pronounce the scope operational. So if anybody is interested in learning how to use that, and especially for doing imaging, it has a phenomenal focal length. I mean, it's 14-inch f10, so you're looking at 3,556 millimeters if memory serves. And it's capable of doing long duration stuff. The auto guiding on it is good. I've managed to exorcise the gremlins that have been haunting it in terms of the firmware as well as the mechanical stuff. And I think we have a fairly operational scope on the go here. It is still an experiment in progress, but I think I can open it up to further training if you're interested. I'm going to post a lengthier note describing this scope and some of its limitations and stuff up on the FLO Google users group there shortly. I'm just preparing that right now. So if you're signed into that, you can expect a message from me on that fairly shortly. And what I'll do is I want to gauge the level of interest that people have in learning how to use that scope, because it's in very cramped quarters right now, and so I'm going to have to limit the groups that the numbers of people that I take through in one group to train it. It's not like something where I can get 20 people out there and show you, do this. It doesn't work that way. It requires a bit of limboing on your part. And it is tricky, but it can do the job. And this is, as I say, this is the Pegasus dwarf galaxy. That was the other challenging object from the previous month. And you can see just the scale of it, given the long focal length, is pretty impressive. Along with capturing a number of small galaxies in various parts of the sky, just like that one, especially that very distant spiral. So 900 seconds, 15 minutes. The auto guiding works well. I was using the ASI 294 MC Pro on this, and I've done some further tests with this. One of the big problems that we had with the scope was trying to get it to aim properly. The internal firmware, I mean, the scope is circa 2001, so it's fairly old. Some of the stuff just doesn't seem to want to work properly, but I've done some workarounds with it, and what I find is that I can now target it accurately, even for objects that you cannot see, and very obscure objects in different parts of the sky. Anyway, I'm not going to go into a lot of details there, but it is possible to target that very precisely now when it behaves. So if you're interested, look for my note on the users group. The next, actually, I'll show the last slide here, which is just another view to show you that it can actually take nicer pictures than the previous one there. That's the Running Man Nebula. This is unlike the last one, which was a single 900-second shot. This is a stack of 3 images. Again, I was doing testing on this, so I wasn't doing my normal paradigm for long duration exposures. So only 3 shots, but it's a combined stack of a 300, 600, and 900-second exposure. Again, showing the quality of the tracking that we can obtain with this thing now that it seems to be working well. So
look for my notice if you're interested, or you can drop me an email at paul.cloninger@yahoo.ca. I really want to gauge the level of interest. That will help me to design the courses going forward, so that that they're useful. And it is not it's not just a turn it on and go type of operation. It is a complex instrument, but it is capable of doing some cool stuff. So I look forward to hearing from those of you that may be interested in learning how to use the beast, because not many of us have 14-inch scopes on the go. Thank you much. Clear skies. We'll catch you next month. Okay, so thank you, Paul. So here are our observing challenges. Our beginners message 72, the intermediates NGC 7331. Our advanced challenge is NGC 1275. And our lunar challenge is Crater Franklin. Thank you to Oscar for pulling those together. Well, those are last month's challenges. There are no challenges this month. You've got a month off. There you go. Okay. Yeah. We can finally say the library is open, and Estelle will meet you behind the curtains back here if you want to come and check out our library. And Estelle's pick of the month will be coming next month, now that we got the library open and we know what's there. So that's great. I invite you to visit the Fred Lossing Observatory. This is for members only, but you can bring visitors with you. And next slide. Our next members only star party is November 11th. We have a waxing crescent moon and hopefully clear skies. Here's the folks that help keep our club running. Next slide. So thank you. We had 90 in the audience today. Thank you to all our speakers. And our we'll move on to the next slide here. Next slide, Chris. Next meeting, December the 1st. It is the annual general meeting, but as I say, it lasts about 30 minutes. And then we do have a couple of presentations after that. So we're going to say goodbye to the folks on Zoom right now. And if you need to get your dinner tickets, please see Oscar or your calendars. I'm going to start calling out the numbers for your tickets for the door prizes. So we'll turn the lights up so you can see your tickets. That helps. And thank you for coming out tonight.